Hello, ladies and gentlemen. This presentation is proudly brought to you by myself, Mafusao Samuel Kofi, along with Awantra Ivy and Osei Emmanuel Theophilus. Today, we are going to walk you through an exciting and essential industrial process, the production of hydrogen from petroleum coke, often called pet coke, and the vital role computer systems play in managing this process. What is petroleum coke? Let's begin this with the basics. Petroleum coke or pet coke is a carbon-rich byproduct of crude oil refining. It looks like charcoal and contains mainly carbon with small traces of sulfur, vanadium, and hydrogen. It's produced during a process called thermal cracking, which breaks down large oil molecules at high temperatures. Now, how do we extract hydrogen from this substance? Let's explore the processes involved. Yeah, let's see the next slide. Process 1: grinding and feeding. Our first process is grinding and feeding. The pet coke is crushed into fine particles, as shown in the picture on the slide. This grinder machine increases surface area, allowing for better reaction efficiency in the next steps. Without proper grinding, the chemical reaction would be slower and less efficient. Let's move to the next slide. Process 2: gasification. Now to the core of the transformation, gasification. At extremely high temperatures, usually between 1200 to 1600 degrees Celsius, pet coke reacts with steam and oxygen. These key reactions occur. These are the key reactions that occur. Carbon reacts with steam to form carbon monoxide and hydrogen. Partial oxidation forms carbon dioxide. The Bordeaux reaction generates more carbon monoxide, CO. And next, the water gas shift produces even more hydrogen. The result is a, synthet- is a synthesis gas, yeah, or syngas, which contains hydrogen, carbon monoxide, carbon dioxide, and trace of gases. Process 3: water gas shift reaction. In this stage, we take carbon monoxide and the syngas and react it with steam in water gas shift reaction. This process increases the hydrogen yield significantly. The balance reaction is CO plus H2O, which gives us the product carbon dioxide and hydrogen. By optimizing this step, industries can maximize the hydrogen extracted from the syngas. Let's move to the next process. Process 4: gas cleaning. Next, the gas mixture must be cleaned. It creates a picture that the scrubber system is used to remove the impurities. So these are the stuffs which are being removed. Sulfur compounds through this sulfurization, particulate matter, metals and other contaminants. After cleaning, the gas undergoes separation, which is done using one of these three methods. Pressure swing adsorption, PSA, membrane separation, or cryogenic separation. Each method isolates hydrogen from the other gases. Let's move to the next slide. So, as chemical engineers, um, normally we decide to put um, what we want to design first on, let's say, paper, so that it will be both understandable to the people who are able to interpret these engineering diagrams and the people who also don't understand. Yeah, so let me take a short time to describe what is happening in this diagram. So the diagram outlines the step-by-step conversion of petroleum coke into high purity hydrogen gas. Here's the breakdown of the stages. Number one, gasification reactor. So in the gasification reactor, inside this reactor, pet coke undergoes gasification at high temperatures here. So in stage two, in the combustion reactor plus filter cooler, hot syngas enters the combustion reactor, then passes through a filter and cooler to remove particulates and reduce the temperature, making it suitable for further processing. Stage 3, water gas shift reactor. So here, carbon monoxide reacts with steam, producing more hydrogen and carbon dioxide. Stage 4, the biodiesel scrubber. This is the biodiesel scrubber. So this unit removes contaminants and impurities. Examples, sulfur or heavy metals from the gas stream. Stage 5, MEA carbon dioxide removal. This is it. An amine-based scrubber, MEA, absorbs CO2, leaving behind a gas rich in hydrogen. Stage 6, pressure swing adsorption. The gas enters a PSA unit where high purity hydrogen, up to 99.9%, is separated from residual gases here. In stage 7, which happens in the steam reheater and recycle loop, any leftover gases are either recycled or exhausted. Some are sent to the steam reheater to maintain process temperature. Stage 8, flue gas to chimney. Waste gases are finally directed into the chimney for safe release. So finally, the system we are seeing right here delivers ultra pure hydrogen gas ready for industrial or energy applications. Let's move to the next slide. So the next slide talks about network types, the kind of networks involved when creating the system. To ensure everything runs smoothly, network plays a critical role. Factories rely on one, local area networks, which is also called LAN, which connects all systems together for monitoring and control. They also rely on controller area networks, CAN, which operate within individual computers to manage devices like actuator or pumps. Regarding structure, we use star topology for centralized control. We also use hybrid topology for flexibility, and we also use mesh topology for reliable communication paths. So in the next slide, computer systems. DCS, the brain of the plant is the distributed control system. The DCS manages everything from temperatures to gas flows. It includes field control units that collect real-time data. It also includes operator consoles for human monitoring and control. It also includes engineering workstations to set system logics and configuration. Next slide. Programmable logic controllers, the PLCs. Alongside DCS, we have PLCs. These are compact computers used for automation tasks like operating a value or triggering emergency shutdowns. PLCs are especially used in equipment such as compressors, safety systems, gasifiers. They also communicate with DCS and SCADA systems, the SCADA systems, forming a part of a smart connected system. Okay, so we're almost at the end of the presentation. So this slide is like a recap on the networks. Yeah, so this slide we this slide talks about the importance of networks in hydrogen production plants. They provide accurate real-time monitoring. They provide efficient communication between machines and staffs. As stated earlier, LANs are the backbone, whilst CANs provide internal control in devices. Yeah. All right. So, and finally, we want to say a big thank you for your attention. Once again, this presentation was delivered by Mr. Mafusa Samuel Kofi, Miss Awuntra Ivy, and Mr. Osei Emmanuel Theophilus. We hope this presentation has given you a clear picture of how hydrogen is extracted from pet coke and the critical role IT and automation play in this industrial process. We are open to any questions. Yeah, is that okay? Yeah, thank you very much. Yeah, bye.